everyone. Today I will talk about my Lab 5 for Physics 2211, the following scanning that I choose on my own for this lab. So for the introduction, the purpose of this lab is first to observe the slinky falling down and experiment with the tracker to analyze the slinky's motion, and then use computational model to analyze and also apply the fundamental physics principles and determine the effect of gravity and drag on the motion of the slinky. So here's some fundamental physics principles that I applied in this lab. The first is about the Newton's second law. So I basically used the net force and also the velocity update formula and position update formula, and also the gravitational forces. So we can also find the gravitational force near the Earth's surface and also the drag force by the air. So the preview of the main result of this lab is that the computational model and the tracker have very similar results. And for this lab, the system is the slinky and surroundings are everything else. So here's some initial conditions. The mass is about 0.24 kilograms and initial position is 0, 0, 0. And video frame per second is 300. Start time is 0 second and end time is about like 5.4 seconds. So here's the analysis of the motion on the tracker. So we can see the professor is kind of let the slinky off, and the bottom slinky is motionless at this period, and the top is like falling. So yeah, the origin I put is on the bottom of the slinky. Yeah, so as the top approach the bottom of the slinky, we can see when they are together, the bottom of the slinky is falling down. Yeah, because this video is reduced the speed, so it's moving really slow. Yeah, but we can see it's moving down right now. Okay. Yeah. So here's the computational model. So first I define the mass and also some initial conditions and about the time and delta t, and also the gravitational force, and also the unit vector for the positive y-axis, and also the drag force constant. So then on the right-hand side, it's about in the first while loop, which is for the time that the slinky's top and bottom hasn't like dropped together. So I define the time interval and also the net force, and also do the velocity and position update. And then continue with the second part, which is when the slinky fall down. So it's kind of the same, but I just include the drag force in here. Yep. So here's the observed and predicted motion that I put together. So we can see it's pretty similar result. So yeah, they're just kind of a little bit off at the end. So there's some possible sources for error, like human error and some like measurement error that can cause that. And then, so what happened in this experiment is that the computational model has very similar result with the experiment, and the net force and the slinky is constant before the top and bottom meet. And we can see that the bottom of the slinky is motionless during the period. At the end, when the motion of the slinky starts to move, both the drag and the gravity act on the system. So why the bottom is motionless at the beginning? I think it's due to the tension of the slinky is the same as the gravity. So the slinky is in equilibrium at that time. Yeah, that's all. Thank you.